Hi, good evening. Today we will continue with another chapter, chapter number 4 on stepper moto. It will be a very short chapter for us to discuss today. Okay, so in this chapter, these are the contents that we will be discussing today. So, firstly, we will see the elementary stepper moto, the effect of inertia in the stepper moto, so effect of mechanical load in the stepper motor and high speed operation of the stepper motor. Okay, so as we can see here, so the elementary stepper motor, our subtopic first subtopic for today. So motor consists of a stator. Stator is like a uh, permanent skin of the stepper motor. So it will be on the top most of the stepper motor. So you usually will have three poles. So we can see pole 1, pole 2 and pole 3 and two pole rotors. Okay, so there will be two pole rotors inside. Okay, so you can see. So there are two poles rotor. Okay, so made of the soft iron. So the winding is connected to DC. So that we can see there are windings. So actually it's not only two wires, so it will be couple of wires that we can see. So if you can open a stepper motor in a physical stepper motor, so you can see a lot of windings of wires inside. So this will be connected to the DC supply. Okay, so we have a supply A, B, and C. So the stepper motor generally will move in a counterclockwise, okay, in 60 degrees steps. So because we have three angles, okay, so it will move in 60 degree step in counterclockwise. CCW is counterclockwise, so it will close A, B, C, uh, then it will go back A, B, C, so it will be counterclockwise. So it's actually in a counterclockwise movement. So the rotation can be reversed by operating the switch ACB, so ACB, so ACB. So this order can be reversed as how we want it to operate. Okay, so that is the elementary stepper motor. So the types of stepper motors. So usually we can see these three types. So variable reluctance stepper motor. So A. So this is the construction. So usually the construction will be different. Some the permanent magnet will be moving. So in some the stator will be moving. So it depends. At times rotor can be moving. So it depends on how we construct the stepper motor. So this is the construction for variable reluctance stepper motor. So it has a winding, it has a stator with pole and rotor with poles. Okay, so this so when the electromagnetic field is generated, it will start to move. Then we have a permanent magnet stepper motor, so B. So we can see there's a permanent magnet in between, and we have a winding stator and rotor as usual. And in some case, so we can have a hybrid stepper motor. So like this. So we have a permanent magnet in between. Then we also have the other types of rotor stators inside. So it can be a combination. So combination of A and B. Okay, so we can have. So usually when we buy hybrid type of stepper motors, so it will be much costly because it has more components inside, and usually it can operate over various applications. Okay, so when we buy a stepper motor, so we need to consider the effect of inertia because if compared to DC motor, stepper motor should be more accurate. in terms of angle. So that's why usually in our projects, so mechatronics projects, so when accuracy and the steps are concerned, we will choose a stepper motor instead of DC motor, because DC motor usually will have slippage. So slippage. Okay. But in stepper motor, we need to consider the effect of inertia. Even though the effect of inertia is minimum compared to DC motor in application, but when uh, a mechanical movement is generated and is moving and suddenly stop, there can be a effect of inertia inside. Okay, similar like how we drive a car, suddenly we press the brake. Automatically, our body will move forward because of inertia. Because the body will try to, uh, it will take some time to forget the movement, uh, and to understand that it's already stopped. So that's why it's very important for us to wear seat belt during the car car accident, car movement. So just for it to protect us from this effect of inertia. So similarly in stepper motor, so we have a effect of inertia. Okay, so we can see in moving pole 1 to pole 2. So there are two things involved. One is the speed and the dotted lines, and also the angular position. Okay, so these two things are interrelated. So the rotor oscillates around 60-degree position before coming to rest. You can see it goes here before it start to slow down. The speed is zero whenever the motor reaches the limit of its overshoot. So it's supposed to stop here, but it goes a bit more to 90 degrees and it started to reach the maximum. So we call it a overshoot. Okay. So when this is over, the angular position is overshoot, you can see time is zero. Yeah, the speed is zero. Sorry, the speed is zero. Okay, then we can see it started to stabilize. Okay, so this is the effect of inertia. We can see it can go a bit further. There can be a case where the effect of greater inertia, meaning the inertia is even bigger. Okay, so same condition with the above figure, except that the inertia is greater now. So we can see, so after 60, it move above 90. So earlier it was 90. It was 90. Now it even moving more than 90, because it is experiencing a greater inertia. So the overshoot is greater. So overshoot, this point is greater, and we can see that the speed will take more time to stabilize, and the motor takes more times to settle down, even though this is in millisecond. So millisecond sometime is still considered fast, but we need to understand the effect of inertia in our application. Okay, so how we can control this inertia? So we can add a viscous damping. So damper is actually like a brake. It's not a mechanical brake, so, but we have some kind like uh, uh, a mechanism to make this effect stop. Okay, so we can see by adding a viscous damping. So it's the same condition with the above figure. Okay, so compared to previous slides, the same, but here we are adding a viscous damping. So for example, we can add a friction for the bearing. Okay, so we can see the effect. So it goes to 60, goes to 60. Earlier it was above 90, but we can see maybe it reached like 65 or 70, then it start to stabilize. So once it start to stabilize, the time also is shorter for it to stabilize. Okay, that's why we need to consider all these elements in our stepper motor. Okay, so another way for us to control the inertia is by using a mechanical load. So mechanical load is some sort like a weight, so something that is mechanical. So that's why we can compare with our car. Okay, when the car is loaded with passengers, so usually it will be the car will be more stable, even because it will press due to gravity. It will press, so the weight will be more on the car, and the car will be more balanced. So similarly, so adding a mechanical load can stabilize the stepper motor. Okay, so we can see this is without a mechanical load. So we can see it take almost 10 millisecond to stabilize. But we can see here, so the shoots are lesser, so no, not much overshoot, and it's already by almost 6 onwards, so it already started to minimize, so minimize and stabilize. Okay, so that's why adding a mechanical load, we no need to do this viscous damping, but we can consider adding a mechanical load to naturally reduce the fluctuation and also inertia. Okay, so these are the things that we can consider in our design. Okay, so torque versus current. Okay, when we are dealing with motor, torque is very important. Okay, torque is the turning effect of force. So how much the rotation can move things, mechanical movement. So like the example I gave before this, the car windscreen, window. So power window. So let's say if you want the motor to rotate to bring the window lower, so it must have enough torque. Okay, if the torque is not enough, the motor will be overheated and it will blow. So determining the torque is very important. In stepper motor, so the torque developed by the stepper motor depends on the current. So meaning more current, more torque. Okay, so it will follow this. Even though this is not a linear curve, but we can see it's almost increasing as the value of current increase. Okay, so let's say we want more torque. So let's say 5. So maybe it's not here, but maybe 4. You need to produce a 16 ampere of current. So this torque is called pullover torque. Okay, so when you produce some input, it will produce a greater output. So that is the pullover torque. Okay, so input pulse high speed operation. So in our daily operation, so one thing that we need to consider is the high speed operation, especially now we have high speed processors, so which can determine a lot of things in fast motion. So we need to have a high speed operation. So it is assumed that the current pulse is in a winding rises immediately. So we always think once we press the button, it immediately increase. No, okay, and when we release the button, it immediately drop. Okay, so this is an assumption, but in practice, this does not happen because of the inductance in the winding. Okay, there's an inductance in the winding, so we need to consider. the inductance L and resistance R in the circuit in the motor, and we need to times it with the time constant T, so which is equals to L. So L in Henry divided by R in ohms. Okay, so these seconds must be added. Okay, must be added before it increase and also before it reduce. So we can see one example here. The coil is connected to the DC source. So we have a coil is connected to a DC source E. So a diode D is connected across the winding to prevent the I induced voltage from the destroying the switching transistor at the moment of interrupt of current flow. So the resulting current as the shape as in the figure. So we can see, so even though we want it to increase here and decrease here, but it actually will take some time before it reach here, and it will need some time for it to reduce. Okay, so this is what usually will happen in the real time, so which we need to understand. Okay, so with this, some input for you regarding the stepper motor. Okay, so hope you can revise and get a better understanding. Okay, so thank you.